Hello, Bill again. Welcome to Module 4 of our seminar. It's on the origins of the modern sign industry. The sign industry and the material selection in our industry is one of the most difficult and the more problematic of all functions that we have in producing signs. And the industry at large has four basic approaches to it, and it's done with a little bit of humor in here, but it can be perfunctory, expedient, sycophantic, and of course there's typecasting. Typecasting means that you're trying to adapt to the typical or the stereotypical image of the business. I use the examples of blue for Greek restaurants, red, white, and green for Italian pizzerias. That's that sort of thing. Perfunctory, this is an action carried out with a minimum effort or reflection. The routine, play-safe approach based on precedents using known standard materials and methods. This is generally what we all do, all sign companies do. Then there's the expedient. That's an action that is convenient and practical, although possibly improper. And I use this as an example at all times. It's that famous trim cap on letters above the recommended height. And this, again, applies that the trim caps were designed for letters not exceeding 36 inches. Yet we always break that rule. It's convenient, advantageous, and completely to the fabricator's interests. All the blowouts and failures that we have above that 36 are legendary. Sycophanting, it's the fear of winning the argument but losing the sale. Flattering the client's ill-advised preferences. That could range anything from the color to the type of lettering. The one most common in my day was if he ordered a 4x20 fascia sign, he wanted absolutely to have a 42-inch letter height, and that, of course, didn't always work. Understanding and correctly identifying the graphic elements, type, color, textures, and shading is critical. Establishing the parameters for reproduction by evaluating the limitations of the subject design from a visibility and legibility standpoint. Here again, the choice of the material and how you put it together will reflect quite often on the letter itself. Define the context of the sign's location architecturally and environmentally. I have situations, and the most classic one is where a survey is taken in the dead of winter, and the sign is located, and then lo and behold, springtime comes along and oops, pops up a tree we never saw before, and the leaves create this obstruction, and the customer comes, you should have realized it. That's just a simple example that I've lived through many times. Appropriate the material which best corresponds to the business identity, funeral homes versus bar and grill. Obviously, you're not going to put a jazzy neon sign for a funeral home, nor an elegant little Times Roman for a bar and grill that is hardly visible. Physical properties, UV resistance, dust and water infiltration, know where the sign is at. If it's close to the ground in a very busy urban traffic area, salt from the roads will go up to the second and third floor. Understand that is something that is easily sold. Being able to convince a customer that you need a material that is easily cleaned and washed, etc. Day and night efficiency of subject sign. Again, here this goes to color and the choice of light sources. Parallel considerations. Of course, people think that we use giant cookie cutters to make these signs. That's not the case. Building a sign for quantity needs study, and you have to design accordingly. Municipal and landlord constraints, those are critical. Those famous heritage sites and goosenecks, you have to factor that in, and how to maximize and take into considerations those nasty shadowing of gooseneck signs, just as an example. Restrictive client conditions, outdated specifications and or graphics. That is a real bummer quite often. You have to factor that in and work around it. And anticipated longevity and servicing requirements. These are all important considerations when you're designing. We cannot begin to talk about plastics, the choice of materials, all the substrates, without starting from the very beginning with the one that's set the standards, and that is acrylic. Everything we do today in signs, even the vinyls, have their roots for establishing values, transmissivity, density, hue. All of it was based on acrylic. The Johnny-come-latelys, the polycarbonate, polyesters, polyvinyls, and the CAB, ABS, etc., they had to be measured against the characteristics of this pioneering stalwart, and that's where we will begin. And of course, it starts right after the war. Plexiglass, as it was known, as was established and registered by the inventors Röhm and Haas. An interesting story about them is after they created plexiglass or acrylic, PMMA, Mr. Röhm stayed in Germany, Mr. Haas was in Philadelphia, and they established manufacturing facilities for the product along with many other sign or rather plastics fabricator, but its chief use was in aircraft as bubbles, as shields and windshields for aircraft. That particular one, for if you are interested, is an A-26 Douglas bomber, and that is precisely what the young ladies are polishing up for assembly. When plexiglass or acrylic was released from the constraints of wartime because it was a strategic material, and of course it was petroleum-based, the industries at large grasped its enormous potential with great enthusiasm. And the sign business, of course, that's why we say the sign business, the modern sign industry started in the late 40s. Naturally, UL and collaboratively UCSA had to establish the criteria for the safe utilization of the very combustible substrate. It became necessary to set guidelines on how to best diffuse the various light sources through plastic within the electrical code and fire prevention parameters. Here's a very simple diagram I've made so that we can just simplify the process. You can understand what we mean by cast. When we cast, we use cast acrylic, which is the first substrate used in signs. It's based on the softening or melting resin syrup, putting melted resin syrup and forcing it and casting it between two tempered glass sheets, varying the thicknesses, of course. Subsequently, it is cooled and then shipped. Resin syrup for continuous cast will go in. Fast forward here, continuous cast was introduced in the early 70s. This is a process where the same concept of pouring continuing the resin through stainless steel belts and then cooling them and polishing them. Here's a brief look at the cell cast principles, how it's made, and then the subsequent continuous cast process. Now, the difference between continuous cast and acrylic in terms of the texture, the optical clarity is a little different, and its deflection is much greater. It's not as stiff as the cast acrylic. And then the subsequent one, the extruded acrylic, of course, has a higher deflection and is a little more problematic when it comes to thermoforming. Well, we'll get to that later on. But here are the first design guidelines for sign illumination. The sign shops adopted the basic UL rule of thumb for sign fabrication, ensuring that the new substrate would not melt, sag, or catch fire. Incandescent lamp would be from the interior of the plastic face was at 12 inches. Mercury vapor, later on introduced, was at 18 inches. Cold cathode and hot cathode fluorescents are the ones that concern us most here, because they are the sellers. For cold cathode, we made channel letters, and with hot cathode, we made fascia signs and double face signs. That 3 inches was the minimum, and the diffusion for that was 3-inch centers. That's the 1-to-1. With hot cathode fluorescence, 4 inches, it's 2-to-1 diffusion ratio. And here is in the diagram, we see the open face channel letter, its origins, And then, of course, the increase by 3 inches to what the classic 5-inch, the standard 5-inch throughout industry, was the addition of that 3 inches and the 1-to-1 ratio. Now, of course, when in self-contained channel letters, that increased to another 6 inches in depth to contain a transformer. We'll fast forward. The 3-inch letter is what we currently use with LEDs, and of course we're getting thinner and thinner, and we might end up with OLED one day, who knows. But the 1-to-1 ratio is the distance times is the equivalent to the center to centers, and for the fluorescents, it's 2-to-1. 2-to-1 is the minimum is 4 inches, and we need proper diffusion 2 times that. We'll go. Here we have the fabrication basics, and these are the ones that establish the constraints that we had to accommodate in signs. In addition to the structure itself, this angle iron structures I will show you in a minute, but the raceways and the shading of the fluorescent tubes, they were very critical in how we made fascia signs, because that shading, that 4 inches at both ends, that darkened with age, and that usually started about 100 days after the life of the fluorescent lamp. We factored that in when we overlapped. We had to overlap the lengths by 6 inches. This here is the configuration that set the standard for many, many years after, until very recently. Again, we're going to stress we're going into a transition from this particular configuration that established it for sheet metal signs, and subsequent to that, of course, the aluminum. And it is based on that 2-to-1 diffusion. 2 times 4 is 8. That was good for interior signs with smaller ballasts. But if you used a larger ballast, you had shadowing issues, plus the structures, so that we had to create a new standard, 12 inches, based on 6-inch distance between lamp and interior face. Times 2 is 12, hence the 12-inch center to centers for all backlit fluorescent lamps. This is where it started, and it established everything from extruded angles, as we'll show you later on. And of course, architectural imperatives established the actual formats of signs. Formats, I mean, the 3x10s, the 3x40s, the 3x whatever. It was always based on what was available above the transom of any storefront. This transoms can be the 24 or 36. Most municipalities would restrict you to 10 feet above ground, so you factor that in to establish the type of sign that you needed in the storefront. I've shown the mall considerations later on, where they also had limitations as to how much of that bulkhead you can accommodate. Wind load was a critical consideration in designing signs, and it also established how we built them and how we retained the faces. And at that time, we attached a lot of importance to surface area and the thickness to accommodate the required surface area. So this is a quick chart that shows you the area of the sign and the recommended thickness to accommodate the wind load factors based on 30 pounds per square foot. Provision for sheet deflection was critical, because deflection can occur as a result of a wind load and gusts, and from the weight of the material when sheets of substantial vertical measurements are resting on the bottom edge. Excessive deflection may permit sign panels to blow out of their frames under high wind load. This is prevented by providing sufficient edge engagement using panels formed to rigidizing shapes. Of course, originally they were all, most signs were corrugated, but ultimately when sign shops were equipped with thermoforming equipment, they could pan and emboss them, which gave it the rigidizing effect. Proper thickness was also very critical. Charts were used to establish what size and what thickness of materials to use. Hanging panels from the top edge allowed for expansion. For the rule of thumb that we used was 1/16 to an inch. We stressed adequate edge engagement. That was the premier consideration of all sign shops. And here's an example, just a quick 120 by 100 acrylic sign face, 2% of 120 inches, the larger dimension, and you arrive at 2.4, or for practical reasons, that usually meant a 2.5-inch retainer. Thermal expansion was usually 1/16 clearance per foot per expansion, both width and height, and allowing 16th for contraction to prevent disengagement. Edge engagement was assured by a hanging strip at the top of the sign box. Flat sheets, the unbraced. My Bible, when I was a young designer, was the Roman Haas sign manual. So I borrow very extensively throughout this seminar from this book, from which all other sign material companies accommodated. The basic design principles: allowance for thermal expansion and contraction. You provide for sheet deflection, structural requirements for sign frames, provision for access to sign interior for maintenance, methods of sealing against weather and dirt, provision for ventilation, and of course, you had to abide by underwriters' laboratories and make sure that all of your connections are properly in conformity. Here are the basic sign design constraints that you had to incorporate into your design, or allowance. You had to provide allowances for these things. Huge, bulky transformers and ballasts, raceways, distance from face. You had housings. You had the high tension GTO wires that you had to suspend away from a metal surface. You had to make allowances for all of these things. Added dimensions to your design. And of course, the aesthetics. You had to frustrate architects who wanted a beautiful Times Roman, sleek, thin, and he could never understand why in certain dimensions he could not have his accents and his letters properly made into a sheet metal form. Induction was a big enemy. You had to design and make and turn and twist 15 millimeter and 12 millimeter neon shapes as closely as you could possibly can without induction, and try and illuminate the serifed areas of the letter. Spot welding tables were of essence, and they were, most shops that considered themselves serious sign shops had one. It was the only way that you could manipulate and make large channel letters and put in and spot weld these components into the back and make sturdy letters. This really involved an electrode that would be in contact with the copper table that would conduct the necessary current to establish that point of that weld point. Hence the word spot welding. This is an example of a sheet metal channel letter that shows the self-contained and enclosed. That transformer would have a little cover for it, and as the law required, you could never put a transformer directly on a sheet metal or 24 or 22 gauge sheet metal. You had to secure it directly onto an angle iron. So that was just an added thing that you had to factor into your design. Making retainers for channel letters was a laborious thing, and it was in the hands of an efficient tinsmith was extraordinary to watch how quickly they could produce these things. They used crimping machines. That was one method. They notched and then backed it and spot welded afterwards. They used to use some type of body filler to smooth it out and sand it, and then spray paint it. And many shops also went by the old soldering system. Galvanized or stainless steel could be soldered in that fashion. This was a spot welding machine devoted exclusively for channel letters and small parts. This gives you an idea of how these letters or these casings were made, how they were supposed to be made, and that was the rule. You had a steel structure that would support all those components and ballasts, and it was wrapped, and that's why it was called a casing at one time, because it enclosed that structure. And the plastic substrate to face the plastic was held on the outside and retained with the formed galvanized angles. The same was repeated, of course, but for a double-faced version. Servicing, it was impractical at the best of times to constantly unscrew and service the faces from the front, because most of them were joined together by nichrome wires, and in the wind and so on, these flat faces would be a devil of a thing to support, because of course once you removed the frame, you had the sheet in your hands. So servicing was used in this fashion. You made trapdoors top and bottom to access the lamp. You had a devil of a time if you had a short and your sockets were burnt out or something. Well, then of course that became a major job. But just to change the lamps usually involved removing the trapdoor and accessing them in very odd shapes, and to avoid those trials and tribulations of servicing, Enden lamps were used occasionally for those that could afford it. And they were quite practical because you cut down on labor in producing a whole bed of or whole line of sockets, and with the spacing that it allowed you, a 9-inch U lamp, for example, you could space 12 inches apart and get excellent illumination. They were popular at one time, but of course they stopped coming into use because not all service people across the country would carry these in stock. So it was a devil of a thing. If you shipped out a sign with Enden lamps and the chap didn't have an Enden lamp, then you'd have to ship a lot. It became a boondoggle, and many sign shops decided just not to use them unless they were forced to. Out with the skilled and in with the quick. That is just it's my take on the difference between, and why I have a certain penchant for the old galvanized or the old method of making channel letters. You have the channel loom right beside it, right on top of it, and the architects loved the fact that with the new channel looms and the trim caps, you had an almost clean face, exposed face. You didn't have that retainer that encroached a half or 3/4 of an inch over your channel letter. With channel loom and letterhead, you had it almost trimless. But the profile of the letter, that 5 inches, would show that bell effect on the corners because of an uneven thickness, so that the letter itself, the can itself, looked distorted. And the back was, of course, became porous and subject to infiltration of dirt much more than the classic sheet metal channel letter. Here's the sort of a chronological, or if you will, evolutionary look at how channel letters evolved. With the classic, with the formed retainers, then the trim caps with the event that became were able to staple when stapling became the method. Then when channel loom and letterhead, the two companies that merged and became channel loom, they used a product called Alumaply, which was a disaster because the edges were never properly silicone and they would delaminate and cause all sorts of problems until today. Today, of course, we use the ACMs, inexpensive ACMs as the back, and we staple it, and it works extremely well with the trim caps. I included the English method for making channel letters because it had an interesting, and it still has, it's a very interesting process. They would solder little copper clips that it would bend back to support the plastic face, and servicing would be done from the back. Thank you, and I'm looking forward to Module 5.